Okay, so this time we're going to take a look at, once again, using the Chrome version of Tracker. It's not as robust as the desktop version. I've got videos already for the desktop version, but I wanted to get people going with the Chrome-based one if that's what you're using. So I've loaded back up Chrome, and I've downloaded the next lab that we're going to take a look at, which is for projectile motion. Now, one of the things that I've taught you all in projectile motion is the acceleration in the x direction is 0, and the acceleration in the y direction is constant, and we assume that to be negative 9.81 meters per second squared, at least near the surface of the Earth. Okay, so I've got everything hopefully set. I'm going to, this time, I've already downloaded the video, so I'm going to go to Select Local File, and I'm going to go to my Downloads folder. Hey, there it is. And then I'm going to go with Lab 3B. Okay, new project, and I'm going to call this TLab, if I could spell that, 003B. And you'll notice that this one says frame rate 120. That's because this one's actually high speed. It's 120 frames per second. And so what we're going to do is to keep ourselves from going insane, we're going to go with frames to move. We're going to go 10. Let's go ahead and give that a try. Last time I told you to leave that at 1. But this time, if you do that, you're going to be clicking for probably the better part of an hour. So let's go with 10 frames, and then we'll see what we come up with. So I'm going to do create. Okay, I'm going to move us forward a bit. And every time I click forward, you'll notice that it started at frame 0, and then it went to frame, let me go back a little bit. Frame 0, it goes to frame 10, frame 20, frame 30, 40. It's actually skipping by 10 frames each time. Okay, here we go. I've got the ball, and the ball is leaving my hand right around here. Let's go ahead and call that our first frame, frame 90. Okay. So I'm going to drag my coordinate system, and I'm going to bring it over here, and I'm going to put it on the center of the ball. With this being high speed, it's not going to blur out, or at least it will blur out significantly less than it has in the previous video we saw. So I'm going to go 90. Let's see. I can actually go back a little bit to 89. The reason that I'm doing this is I'd like to find the point right when it's leaving my hand. So I'm going to drag this forward a little bit. Looks like 92 sounds good. I'm going to go ahead and grab it here. 90 should be fine, but I like to make certain that it has left my hand. Because if it's in my hand, I'm applying a force to it, is a preview of things to come, it would seem, and that imparts a different acceleration. I'm speeding it up to throw it up in the air. And what we're talking about will only be the case, the accelerations that I mentioned earlier will only be the case when it's flying through the air. Now the next thing I want to do is I want to drag this forward some. And I'd like to get it where it goes up and maybe comes back down mostly. So I'm going to drag this back over, and we could call this frame 176. What did we start on? Looks like I can drag that independently. 92. So let's go in an even step of 2s. 181. There we go, 182. I don't know why it wasn't dragging with it earlier. Okay, so we've got quite a bit of the motion here, which is good. All right, now we've got that set. You'll see that there's a meter stick taped up in the background. So let's create a scale. Blue seems fine. I'm going to click here, and then click on the other side, and then type in 1 meter. Again, you can drag these if you didn't get them quite where you wanted them, but this looks pretty good to me. Okay, great. We've got all of that, and now I just need to do a track. So let's see, here we go, create new track. And I'm going to call this track A, create. And bright green seems good enough to me. I'm going to click in the middle, and let's see. Now you'll notice that it jumped from 92 up to 100, it seems. So that's fine. It didn't quite do 10, but that's okay. Then it goes to 110. I'm going to click on the center of the ball to the best of my ability each time. Now, in the desktop version of this, I walk you through how to do an auto track, which is also a great way of working with this. You get a ridiculous amount of data, but I don't think that this Chrome port has that capability. So here's where we're going to do setting it up to jump by a couple of frames each time. And we can see that we're still tracking the motion. And when you look at it, we can actually see that we've got a parabolic shape here, which is another thing we talked about in class. All right. Let's see what our data looks like. So I'm going to do Control A so I can copy this. Might have been worthwhile to do maybe 7 or maybe even as low as 5 frames per jump, but 10, we'll see what we get with 10. All right, here we go. I'm going to paste this in. Once again, mine isn't copying that, so that's T. Ooh, this time we need both X and Y, and we want to keep track of which one is which. I certainly hope I got my camera set up properly. Now, we're not actually going to engage in any linearizing on this, at least not right away. The biggest thing that I want you all to see is the assumptions that we've made up to class in regards to projectile motion. In the X direction, I told you that we can assume that there is no acceleration, it's 0 meters per second squared, and in the Y direction, it is negative 9.81 meters per second squared. So let's see how that turns out. So here we go. Let's start off and do insert a chart. We're going to go scatter chart like usual. And this time I'm going to do a position versus time graph in the X direction. Now, if we have no acceleration, then that means we have a constant velocity, which means we should end up with pretty much a straight line for our data. And as you can see, well, that looks pretty much like a straight line to me. All right, make certain that row 2 as headers is not selected for whatever reason. Customize, make certain under series that you don't have, oh no, sorry, it was under horizontal axis. Don't use treat labels as data, which is weird also. Don't know why it turns those on from time to time, but nuts to it. Trendline. Let's go ahead and get our trend line, use equation on chart. Looks like when I threw this ball, it had an initial velocity in the X of 3.23 meters per second. That's my slope of this position versus time graph. Now let's give this a title because you're going to be turning in 2 graphs to me. So title, Sanchez, X, or we could call this horizontal position versus time. Great. And then we want our horizontal axis. We want to label that time in seconds. Great. And then our vertical axis, horizontal position, meters. Technically meters is lowercase. I held down shift too long. Okay, great. Here is one of the graphs that we want. And with this, we've actually made a measurement that my initial velocity in the X is 3.23 meters per second because that's the slope of my position versus time graph here in the horizontal. So this is one of the graphs that I want. Okay, great. Speaking of which, let's go back up and label our TALB TLAB 003B Sanchez. Great. So that way when I share it, or if I need to go find it again later, I can easily find my document. I'm going to move this graph a little out of the way, click back out in the middle of nowhere, because if you're on some numbers, then it'll try and get smart and predict what graph you want, but it's always bad at that. We're going to go scatter, and we're going to go series. Let's take a look at the Y direction this time. Okay, so we've got Y, and then we need to add a horizontal axis, which is not the X values, it's going to be our time values. We want a position versus time graph. Great, once again, check for the usual suspects. Use row 2 as headers should be off, and then treat labels as text should also be off. All right, here we go. Let's go Trendline. Does that look like our data? I hope you are saying no, that does not look like our data at all. We've got what appears to be a parabolic shape to it. It's got a nice curve to it. It is very clearly not linear. So we can come down here to the type, and we can actually go to a polynomial. That is a pretty nice fit. Okay, so let's see what our equation will look like. Now, real quick, I'm going to point this out. I do want this, but I'm not too concerned about getting a clear measurement on this. What we can see here, we talked a little bit about this in class. This should be not x squared, that's the horizontal, that's what it's telling me, but that's actually time squared. So this should be 1/2 of my acceleration, because that's what's multiplied by time squared. We're getting about -6, so our measurement for the acceleration due to gravity here is about 12 meters per second squared. One of the things I'm going to bring up is I had to throw the ball in the hallway, and the meter stick is taped to the wall behind it, so part of this may actually be that our scale is a little off because the ball is a little bit closer. That being said, I'm not going to track that down too much. We still get the main idea here. I can also see that my initial velocity in the y, according to this equation, because that's what's multiplied by the t, is positive 3.96 meters per second. In fact, now that I have the y component and the x component, I can also find the angle at which I originally launched this, at least based on these points being my initial position. The most important point that I want to get across on this is we do have a parabolic shape. And not only is it a curvy line, which tells us that we do not have a constant velocity, and indeed have an acceleration, we can actually do a fit for our trend line, and we can actually get, once again, a measurement of our acceleration due to gravity. No, it's a little off. And there are a couple things that we can tell about this. For those of you that have studied these sorts of things with the shape of the graph, it is concave down, which tells us that our second derivative is negative. In other words, our acceleration, which is the second time derivative of the position, is actually a negative value. Anyway, that's a little bit of extra information. Let's get this finished up. I'm going to click on this graph, not that I was ever off of it. We're going to go over to our chart titles. I'm going to go back up to chart title, and I'm going to say that this is Sanchez position, vertical position versus time. Great. Now that I've got that, let's go with our horizontal axis. We're going to go with time in seconds. And then our vertical axis is going to be vertical position in meters. Okay, great. And now that we've got that, we've got pretty much everything that I want. Hopefully I've spelled everything correctly. Okay, biggest things that I want here are both of these graphs, and that's the main thing that you're actually submitting. And from this, I want you all to understand that one of the things that I've told you in class to just accept, we now have a direct measurement of. We can see that there is no acceleration in the x direction. We have a nice constant velocity given the constant slope of our position versus time graph, and we can even measure that, at least insofar as our measurements are precise and accurate. Again, I think my meter stick might be a little off. And we've got a vertical position versus time, which has a parabolic shape. It actually has an acceleration. We can see what's going on with this. All right, so like usual, go up to share, get shareable link, and then copy link, and then you can paste that in, and I should be able to see that. If we're having any problems, just check back, let me know, and that should be good. Okay, that's the second track.